Thank you. Thank you. It's really a great honor and a privilege to have been invited here to this conference in honor of Emmanuel. And it's also been an honor and a privilege to have been here at the IHES. I first arrived at the IHES roughly 3 years ago, and it's remarkable how quickly it's gone. And I think because the time passes so quickly, it's easy to overlook just how seamlessly and efficiently and elegantly things are run here. And I think there's very few people, very few mathematicians certainly, who are capable of running such a large and complicated institution, certainly not as well as Emmanuel does. And since we know it's of course very difficult to produce great mathematics, but it's also very difficult to enable other people to produce great mathematics, and Emmanuel does both. So I think that's very special. So as was mentioned, what I'd like to talk about today is some applications of unlikely intersections, including work of Emmanuel's to integral geometry. So I'm going to start by stating 3 theorems. The first of these 3 theorems are joint with Ziquan Yang. And the basic idea of the 3 theorems is that I want to illustrate that there's all sorts of kind of positive characteristic statements that one can prove about moduli questions for large enough primes, which ultimately reduce to a kind of common toolkit coming from Hodge theory. So I'll write that. So we state 3 theorems. To illustrate a common method. And then first 2 with Ziquan. So the first theorem is about lifting isogenies, or really lifting isogeny decompositions of Jacobians. So I'm going to state things here in the very simplest case and just kind of explain orally how this stuff generalizes. So let's write theorem. Let C be a general genus G curve over Fp bar with P much bigger than 0. And suppose we have an isogeny decomposition of the Jacobian of C, E cross A prime, E an elliptic curve, of degree prime to P. Let's write it maybe a little lower. Then all the data lifts to a finite extension to, let's see, OK, where K is a finite extension of the width vector ring, and then we take the fraction field. Okay? So to summarize, everything lifts to characteristic 0. That's what it says. So let me make a few comments about this. First of all, it's not very difficult to lift curves to characteristic 0. And if you start with, let's say, an ordinary curve, mod p, and you look at its Jacobian and you have some endomorphisms of that Jacobian, you can certainly lift that Jacobian to another abelian variety together with the endomorphisms. There's something called the canonical lift of that abelian variety. You can lift the abelian variety, all the endomorphisms lift as well, and you get some other abelian variety with the endomorphisms. The difficulty here is that this is saying that all of this lifts, but you can also lift the Jacobian to a Jacobian. So somehow you are doing a lifting question, but along the moduli space of curves, not necessarily in the ambient space AG, but you are lifting along the locus where everything is a Jacobian.
So general means that you work on some Zariski open?
Yes, so there is a Zariski open, and inside the Zariski open, if you have this data, then everything lifts. And actually what will be true is that this Zariski open can be chosen integrally. So it doesn't even depend on P for P large enough.
Okay, and if you have an extension, algebraically closed extension of FP bar, and you have the same is true for WK, that is, if you take a situation of a small k in the Zariski open with the isogeny decomposition, then it leads to WK 1 over P, or is it something where you...
Sorry, it lifts to OK.
No, suppose you have something, not FP bar, but other points, and maybe it follows trivially from the statement.
So you want to lift over a more general field. Yes, these kinds of results will also be true. But yeah, I just want to say it in this case for simplicity. Yeah. OK. So that's theorem 1. So theorem 2 has a very similar flavor. This is also with Ziquan.
So do you have some kind of effectivity of P with respect to G?
I mean, the term effectivity kind of always means nothing to me. I mean, in some sense, I don't have a formula. I can prove there exists an algorithm that will...
Same as you don't.
Well, it's effective, but you know, you will never run this algorithm. So it's the...
That's for engineers.
Knowing the existence of an algorithm is not the same as knowing an algorithm.
Sure, I know the algorithm. All right. So let d greater than 5 be an integer. If p greater than 0 and c in pick y is a line bundle for y contained in P3 FP bar, a general hypersurface then yc lifts to characteristic 0. Characteristic. I'm not trusting my spelling. All right. Car period 0. D is the degree of the hypersurface, yes. So hypersurface of degree D. Okay, so lifts to characteristic 0 here means in the same sense. There's a finite extension, and if you look at the ring of integers, you lift all the data to the ring of integers. Okay, so this is theorem 2. And finally, theorem 3, which is a bit more technical. And I probably won't get to it, but I just kind of want to state it because somehow, although these two applications are very nice, the statement of the third theorem is kind of more at the heart of the method. So theorem 3, let f x to s be the universal family of degree, and I haven't given the most optimal bound here, but I just picked one that works, d greater than 9, hypersurfaces in P to j plus 1 then the union z z in fp bar, and then we can take a union over p as well, such that z carries an exceptional family of middle cohomology divisors is not Zariski dense. Okay, so there's a lot of work being done here in my language. Let me. Yeah, Z in S sub FP bar. Thank you. And then here, I think I also want J bigger than 1. Over Z. Yeah, so maybe I should write this is Z, and then J is bigger than 1. Okay, so what is the connection between these three results? So first of all, maybe let me explain what I mean by exceptional family of divisors. So somehow, when you look at the families of the cohomological objects that you get from a hypersurface variation, typically all of the interesting things happen in middle cohomology. And there is a kind of universal divisor class that sort of, once you separate that out, you get a kind of primitive piece. And then what I'm asking is that I'm going to look at loci in S, where over that locus, I have a divisor inducing classes in middle cohomology, which is giving you at a generic point some additional algebraic de Rham cycles that are in addition to what you get from the global primitive class. And what I'm saying here is that actually this doesn't happen, with the caveat that you have to exclude those varieties that lie inside the fibers of the natural period map. So somehow there's this equivalence relation that comes from the fact that if you take a hypersurface, you can act on the coordinates with some linear transformation, and you get another hypersurface that is isomorphic. It's technically different in the sense that the coordinates are different, but it's basically the same thing. You can look at those orbits, and you can construct all sorts of families over that, but that's not very interesting.
Is it in projective space of odd dimension?
Yes.
And now a divisor gives something in middle cohomology.
No, not a divisor, sorry. An algebraic cycle.
Not divisor, so you don't mean divisor.
I don't mean divisor. I was confused by, I was thinking about this case and I just said divisor. Algebraic cycle.
Okay.
Yes.
Cohomology.
Yeah, this is, wow, that's amazing. All right. F carries an exceptional family of algebraic cycles algebraic cycle classes in middle cohomology.
From the obvious middle cohomology class. Okay.
Yeah, nothing fancy. And so this is in some sense an unlikely intersection problem. The reason being that if you think about the Hodge-theoretic period maps that Ben was talking about, the way that you would construct these kinds of exceptional loci in characteristic 0 is that you would take your base, you would map it into the period domain, and then you would intersect with something. And what's known, thanks to work of Emmanuel, Bruno Klingler, and Greg Baldi, is that in this setting, at least in characteristic 0, all of these loci that you get over the complex numbers, if you take their union, they're actually not Zariski dense. And somehow what I'm doing here is I'm showing that actually for large enough primes, this kind of thing even holds in positive characteristic. And the reason that that's important for the lifting questions is that it turns out that the lifting questions are also related to unlikely intersection problems. Somehow because when you want to lift these classes, what you want to do is you want to look at, say, the moduli space of curves inside AG, and you want to intersect it with a sub-Shimura variety, and you want that intersection to have characteristic 0 points. And the idea is that it should have characteristic 0 points as soon as the dimensions are big enough that the intersection should exist. And moreover, if it doesn't have characteristic 0 points, in the case where the dimension is big, you get a bigger intersection mod p, because the intersection only occurs mod p, and so it's bigger than you would expect. And so you can somehow rule out the bigger than you expect dimensions by putting them in a locus like this. So that's what I'm going to try to explain.
Excuse me, what does the P in double index mean? You have a union of Z?
Well, because I'm taking the union over all things in S FP bar, but I'm taking the union over all P as well.
Yes.
Does it fail for degrees that are smaller than 9? I'm just curious about this.
Yes. Well, not for all degrees that are smaller than 9, but somehow if you pick D small enough, this statement will fail.
And 9 is optimal?
No. 9 is optimal in the sense that it was the easiest thing to write that without going into special cases.
So do you understand precisely the locus which is not the reduction mod P of...
Can you say it again?
Do you understand precisely the locus which is not the reduction mod P of what happens in characteristic 0?
Yeah, that's all I want. Okay. Good. So what I've sort of explained orally is that ultimately this kind of thing will come from Hodge-theoretic intersection results. So I'd like to say a few things about Hodge theory. So Greg will, I think, go into more detail about this sort of thing, but I just want to cover the broadest sort of version that I need for what I'm about to say. So we'll do unlikely intersections in Hodge theory. After BKU.
So in this theorem 3, you need to know that something is exceptional, but is not in middle in the. But in characteristic P, you can use a Laddick homology, but then you have independence of L powers.
Yeah. So using positive characteristic Durham cohomology is ultimately where these classes. So they have to be non-zero there, and they have to be exceptional in positive characteristic algebraic Durham cohomology.
So mod P, yeah.
Mod P, yes.
Okay.
Okay, so let's recall. Given a smooth projective algebraic variety Y over C, the cohomology groups HI, Betty, and let's say mod torsion, carry the structure of a polarizable integrable polarizable integral Hodge structure. I won't say much about the polarizations, although they are important. I'll just remind you briefly what a Hodge structure is. So this means if we take this and we say that this is V, there is a decomposition VC equals sum over P plus Q equals I HPQ with HPQ equals HQP bar, and HPQ spanned by harmonic forms of type PQ. And importantly, if the varieties come in a family, F mapping X to S, we get a variation of Hodge structure which is a triple that I'm going to write as V, F, well, no, I'll write it as a pair actually, where V is Ri, Fn, Z, and F is locally given, so F is a filtration, and F is locally given by, well, not even locally. It's given by Fr is sum over P greater than R H PQ. Okay, so this is very standard. And what's important for us, importantly, the data V, so I'll explain this V in a moment, FV nabla. So here V is this tensor product. So basically you take the local systems and you form the vector bundle. Nabla is the natural connection. Admits a natural algebraic model. And then I'll write here Duram model, which makes sense over rings of integers of number fields if F does. So somehow there's this algebrogeometric incarnation of all this data that we can work with instead of the variation of Hodge structure. And so a lot of what we're going to be doing is we're going to be looking at results that Emmanuel proved with Bruno and Greg and reinterpreting them in an algebraic situation, algebrogeometric situation, using just this data. Okay, so we also have period maps. So VF induces a natural map from the analytification of S to D mod gamma. So D here is the classifying space of all polarized Hodge structures on a fixed, let's say, with fixed Hodge numbers. And gamma is basically group of symmetries of the data. So it's just really integral elements of the group that preserves the lattice in the form. And in their paper, Baldi, Klingler, and Olmo study a notion of atypicality for such period maps. So what's important is that we can embed D into D check. So this is an open embedding. With D check, an algebraic of polarized Hodge flags. So somehow when you have a polarized Hodge structure, there's sort of two natural compatibility conditions that the Hodge structure has with the polarization. And one of them involves an equality, and the other one involves an inequality. And the one that involves an equality is algebraic. So you, in the subvariety of all Hodge flags, you get some algebraic subvariety D check. And the one that involves an inequality defines an open set, which is this one. So we then consider intersections, or let's say intersections arising in the following way. So we take Sn. In here, we take some little ball, and then we choose some holomorphic lift to D of this period map. So here we have phi. And what we're going to do is we're going to take this D, it's going to lie in D check, and inside here we have some Y. And what we're going to do is we're going to consider intersections of psi of B with algebraic Y. And the point is that some such intersections are going to be called atypical. And so this kind of situation arises all the time when you're doing Hodge theory and defining Hodge loci. So somehow whenever you have a Hodge vector and you want to look at all the Hodge classes, all the Hodge structures that have that Hodge vector inside the middle piece of the Hodge decomposition, that is an algebraic condition on this variety. And so when you want to study the locus in B that has this algebraic condition, naturally what you do is you look at all the Hodge structures that you get and you intersect with that variety and you want to see what happens. And basically what we want to say is that such intersections, when they're too big, they don't happen except in some kind of Zariski closed locus. And the very interesting thing about the theory is that it applies to any algebraic Y that you work with here, not necessarily one that has a kind of Hodge-theoretic interpretation. Okay, so that's the, I'll maybe keep the theorems. Maybe I'll start here again. Okay, so for consistency with my notes, I will understand this intersection in terms of the pullback of Y inside B. So as a definition, we say a component C contained in psi inverse of Y is atypical if the dimension of S minus the dimension of C is less than the dimension of D check minus the dimension of Y. So the codimension is smaller than you would expect. And what BKU proved and so this is a kind of reformulation, but it follows from the methods in their paper, is that if you assume the monodromy of V is as large as possible, or so maybe I should say the Zariski closure of the monodromy of V is as large as possible, and G, Y to Z, is an algebraic family of subvarieties of D check of dimension greater than dim D check minus so basically these subvarieties have to be large enough such that these intersections are always going to be positive dimensional. That's what that condition says. Then this union, Cy, Y, a fiber of G, and then Cy atypical, is not Zariski dense. Yes. Okay, so somehow when I wrote the third theorem, I had this kind of union of all these things defined by seemingly Hodge-theoretic conditions. I wanted it to be not Zariski dense, and this is a kind of prototypical statement of this type over the complex numbers. How much time have I used instead of 30 minutes? So I have another 30 minutes. Yes? Yeah, okay. Good. All right.
Just to be sure, in theorem 3, the Z is positive dimensional. You don't need
yes, so what I said, I kind of cheated a bit by trying to subsume everything in this sort of exceptional family of algebraic cycles condition. So in this case, the positive dimensional condition is really that you don't lie inside an orbit of the natural action of a linear group on a hypersurface. So basically there's, if you take a hypersurface, you can pull back the coordinates by a linear action and get the same hypersurface in some sense. If you look at those orbits and your z does not lie in one of those orbits, then it's kind of allowed to be in this union. The ones that lie in those orbits we don't include. And so that's the same thing as basically this condition, as that period image in the Hodge-theoretic setting being positive dimensional. Okay, so then the question now becomes, all right, how are we going to interpret this over z? So let me tell you a few things about jets. So somehow, I've given you something that is somehow very complex analytic. And of course, one of the difficulties in studying these sorts of variational questions in positive characteristic or in p-adic settings is that you don't typically have good analogs of period maps. But one of the sort of insights of this whole approach is that a lot of these questions are really very local. So somehow here, when I formulate this condition, even though the loci that I'm trying to control, the sort of the algebraic loci in the base that I'm trying to control are typically algebraic, I'm actually controlling all analytic germs that I get when I intersect inside the flag variety with a certain subvariety. And it'll turn out that even more is true. So it's not just the case that you can control all the different analytic germs that you get by intersecting images of period maps with algebraic subvarieties of d-check, but you can even work with just infinitesimal germs. So what I mean by that is if you tried to write down a period map, what you would do is you would start with the Gauss-Manin connection. It has some kind of algebraic form. You can solve the connection to find some power series solution to sort of locally trivialize your local system. And you can keep solving it to higher and higher orders. And in characteristic 0, you get, you can construct an actual flat frame, and you get some power series. And in positive characteristic, you sort of get stuck. Because at some point, when you write down these power series that are supposed to solve the Gauss-Manin differential equation, you're going to have to divide by p. And so you'll end up with some p's in the denominators, and then you can't do the kind of period map construction. You can't make the same definition. But you can do it up to an order r that is less than the characteristic of the field. So you can always take the Gauss-Manin system, and you can compute all the derivatives up to p minus 1. So if p is 7, you can compute it up to order 6. And you can look at those infinitesimal objects, and you can say, well, that's an infinitesimal period map. It maps infinitesimally to the flag variety. I can ask what happens if it sort of intersects infinitesimally in some precise sense. And is it the case that all of that stuff is controlled by an algebraic locus? And the point is that there is a finite order at which that is actually true. Okay. And so I'm going to try to make that precise. And once we make that precise, we will have the analog of this kind of statement, but in the integral world. And then it will control all the loci that we care about.
What is this monodromy as large as possible?
It just means that, like, basically, if I take, if gamma mon is my monodromy group, it maps into the automorphism group of some fiber fixing some polarizing form, and it means that this closure, the Zariski closure, is equal to this. So basically, the monodromy is big in some sense. Like, for example, in the abelian case, it's the Zariski closure of the monodromy is sp2g.
Okay, just using those things, not for the other Hodge tensors. Only the polarization.
Yeah, just the polarization, yeah. So the polarization itself defines the Zariski closure of the monodromy.
Yeah, which means that there are no other interesting. Okay.
Yeah. Okay. Good. So I was going to tell you about jets, so let's do that. So let's recall for any quasi-projective scheme over R with R a ring, and each pair of integers dr greater than 0, let's call this scheme X. There is a scheme JDRX that represents the functor JDRX T is HOM over R T cross R D dr x, and I'll define this space for you momentarily. With ddr equal to spec r t1 td modulo t1 td to the r plus 1. So if you've seen jet schemes before, usually people consider d equals 1, somehow because it's more convenient. In this case, we're going to want little d to be the dimension of these atypical intersections. So it helps to consider these kind of higher order jet schemes, where basically what we're doing is we're parameterizing all the possible maps from the d-dimensional rth order unit disk into our space. And basically the way that you construct this scheme is kind of as you'd expect. In the affine case, you just kind of write down in coordinates what you want such a map to look like. And if you sort of have the map go into a locus defined by some algebraic equations, you just expand out those equations and you get the necessary conditions on the coefficients of the jet. Okay, and then I think it's finally time to use the main board. I don't know why I'm holding this. Oh, I know why. And so what we're going to do is we're going to use these jet spaces to construct a kind of big algebra geometric object that lets us study infinitesimal period maps. And so I'm going to state a big theorem that is basically a kind of big construction. So let's say theorem. Using the data V F nabla, we can construct over R 1 over R factorial. So this is going to correspond to inverting the primes sort of in the denominators of the infinitesimal period maps that we construct. So that's, you're constructing things up to order R, so you need denominators up to order R. A G equals Zariski closure of monodromy. So this has to be interpreted in some kind of precise de Rham sense. Map P dr alpha dr j dr d check. So this d check is a variety. You can make sense of it as a scheme over Z. So certainly you can consider it in this setting. And here, PDR, is basically the pullback of the frame bundle. So remember, this is my algebraic de Rham cohomology. And so then I consider, let's say, frame bundle of V. This maps to S. There's a natural projection like this. And so we take this fiber product. And so basically, you construct the variety whose points are frames of V above some point in S, and also jets at S. And basically what you want to do is you want to take the data of a frame and a jet, and you want to map it to a jet in here. And this map acts on points by, you have a jet and a frame. So here, M is the rank of V, and it maps to psi after J, where psi is the rth order period map at S determined by the frame. All right. And so somehow this is also equivariant under the monodromy group, or if you like, the sort of natural group of symmetries that preserves the fiber and the polarization, in the sense that if you, I mean, these frames they should really be thought of as polarization preserving frames. So this D check, so I mean, D check is some kind of scheme of Hodge flags on some VQ, where all this data makes sense integrally. And so this frame is also a frame that preserves the natural polarization that's on here and the polarization over there. And so if you look at the group that acts on all of these frames, you can act here on a frame, and then you can act here on the resulting Hodge flag that you get, and this map is compatible with the action. And so another way of saying this
So you have a vector bundle, so you just look at the base. I am a little bit lost. Is it a basis or just a more?
Well, it's a frame, so you can think of it as a basis, yeah? I mean, it's the same data in some sense. Well,
but what is it related to all the data, the Hodge? It's not, is it related to the variation of Hodge structure data? Or?
Well, so the variation of Hodge structure, I'm assuming that there's some polarization in the background. And so this fiber here is polarized. And this here, I mean, this V, if you like, I can think of it as just Zm. And so it also has some Q. And so this isomorphism is compatible with the Q here and the Q on this field that is induced from this Q.
Well, S is a particular point.
Yes.
Okay, so it is just preserving the polarization and not the filtration.
Not the filtration. Okay. And so, as a kind of remark, one can think of this data as a map of Artin stacks eta dr JDRS to JDR D check mod G, where G is my group up there. So somehow it's a period map, but it's you sort of construct period maps, but of course you have no periods because you have no integral lattice, and so you only remember the derivatives. It's basically the idea. And from this, we're going to construct these Baldi-Klingler-Omo loci. So let's explain how to do that. So the idea to construct a locus containing these unions of CYs. So this is as before. I'm not going to write down all the conditions. A tip we can consider ER, and so what we're going to do is we're going to take an image of all of the different jets that you can get that are pulled back from varieties Y inside D check. And we're going to choose D, the little integer D, so that this is atypical. So we're going to consider this eta dr. We'll take the inverse image. We'll look at JDR Y. So I'm only considering one Y here, but I'll explain why in a moment. And we're going to intersect this with jets that are non-degenerate. So somehow, when you're doing this kind of thing and you want to understand whether or not a certain disk maps into Y, it doesn't really help if the disk that you have is degenerate. So inside this jet space, inside JDR, there's a kind of space of non-degenerate jets, which are just those jets that induce open embeddings. So basically, they're injective on tangent spaces. So we're going to intersect with that. We're going to map all that to S. And then we're going to take the Zariski closure of this. Okay? So a priori, this is just some constructible set. So constructible in the scheme theoretic sense. And you can take the Zariski closure, and you get some kind of subscheme. And so over C, we know that if I take the intersection over all R, ER, so this is, let's say, E, this is going to be equal to ER naught for R naught much bigger than 0. Okay, so this is just a trivial fact about closed sets in Noetherian topological spaces. But somehow the point is that what you're doing here is you're considering these sort of intersections for higher and higher order. And what I want to claim is that the situation where you know that you have a kind of atypical intersection that comes from a period map that is really sort of complex analytic is captured at some finite order. And the fact that it's captured at some finite order is somehow captured by the fact that these intersections stabilize at some finite order.
What is the subscript of JDRS in the formula?
It's ND. It's just the letters N and D, and ND is non-degenerate. And it means that the map of the jet, so if you look at DDR to S, on tangent spaces, this is injective.
Okay.
Do you need to multiply with the group G somewhere in this ER definition?
Here, do I need to involve the group G? Right, so I was about to explain that. So part of the sort of the interesting thing about this, I mean, is that this map is G invariant. And so when you pass to this quotient, there's a G here. And so secretly, this expression doesn't make sense because realistically, what you need is JDRD check. I mean, and so I'm really taking the image of this in this, and so there's actually a G here.
Okay. Yeah, so that could have been written more clearly, actually, but
There is a G.
Yeah, so let's maybe one way of writing this more intelligently is just to put this, define some pi, and then put pi here. So that this JDRY is actually inside this space because a priori it's here. Does that make sense? Okay, so I think probably I should just use these blackboards. Okay. And so a proposition, which I will just kind of, I will explain the proof of it in words because it's a bit technical, but it's not necessarily that deep. So the proposition is that the locus E agrees with the same locus in the BKU theorem for the family. And so this proposition is taking place only over the complex numbers. For the family G, Y to Z, where Y here is, it's all the varieties of the form little g times Y, such that G is in GC. And this is just, I mean, if you like, Z equals G. Okay? So if you apply the statement of the BKU theorem, I had it taking as input some arbitrary family. And maybe I should write here, after choosing G, after choosing D of appropriate atypical dimension. I'm ignoring some minor technicalities here because in principle the different components that you get could have different atypical dimensions, and so I have to vary D and take some kind of union. But let's just assume for now that they're all atypical of dimension D, and then once you do that you get exactly this locus. Now the advantage of doing things this way is that everything here has been produced using some algebra geometric construction. And we've learned from the situation over the complex numbers that actually you don't need this infinite intersection, but you need just some kind of finite intersection before you're no longer Zariski dense. So as a corollary of this, the locus E R naught defined in the same way over R. So R, if you like, you can take R to be Z in our examples. 1 over R naught factorial is not Zariski dense. And the point is simply that this whole construction is compatible with base change in the ring R. And so ultimately, it's just a kind of fact that if you take some scheme, like inside a subscheme, inside a scheme defined over Z, if the generic fiber is not Zariski dense, then the scheme isn't either. Okay, and so the last thing I want to do is I want to tell you how this resolves the lifting questions. So originally, I gave some applications. So let's return to at least the setting of theorem 1. I'll try to explain. Okay, so in the setting of theorem 1, we have S is mg, d mod gamma, this is ag, d is the upper half plane, and y, you can take it to be hg minus 1 cross h. This embeds naturally in here and also into the natural compactification of this space. And so then you just take the Zariski closure of that. And what do we take D to be? Let me reference my calculation, which is somewhere. Right.
D is the bigger upper?
Yes, but there's also a little d, is what I wanted to say. So if C is a component,
Y lies where?
so Y lies in the natural compactification of this. So if you take this, there's some embeds in D check, and this Y is the Zariski closure in D check. So if C is a component of mg intersect T, where T inside AG is a sub-Shimura variety parameterizing abelian schemes with a fixed prime to P, isogeny to some product E cross A prime, then T is LCI defined locally by G minus 1 functions. Okay, and so what we'll do is we're going to take D to be large enough so that if you have an intersection, if the intersection has a codimension at most G minus 2, it's already atypical. So D is going to be taken to be G plus 1 over 2 minus G minus 2. Okay, period maps we can erase. Now we suppose the reduced locus of C is contained inside, so let's write mg fp bar then the codimension of mg in mg fp bar of C is less than or equal to G minus 2. Okay. The reason is simply because in the ambient scheme, when you look at this intersection C, when you look at this C inside here, this is some scheme theoretic intersection over Z1 over R factorial, or sorry, let's say it's an intersection over ZP for P sufficiently large, then that intersection has codimension at most G minus 1. And so at least one function is needed in order to put this, subscheme inside here. And so there's only G minus 2 functions possible left to cut out C. And so here, when you look at C sort of inside this moduli space of curves, it becomes atypical mod P, if the reduced locus of C is in an entirely mod P thing. And so by the construction of E, this means C reduced lies in E. So here it's actually important that I'm using this prime to P condition, because ultimately, in order to construct these local period maps and in order to satisfy the fact that I land in a certain flag subvariety, I'm going to need to be able to see this algebraic cycle condition in the positive characteristic algebraic de Rham cohomology. And so that's why I use prime to P isogenies, and so that's kind of where that comes in. And so this means, so as a consequence, sorry? Okay, I'm finishing right now. Consequently, if C, the reduced locus of C is not inside E, then C has characteristic 0 points. And that's basically, as a very first step, that's what you need in order to lift. The way it really works is that you show that C is LCI, and when it has a fiber both in characteristic P and characteristic 0, then it's flat by miracle flatness, and then you can use that to lift. But ultimately, it comes down to this dimension condition. So I'll stop there. Thank you.
So maybe just one question. Okay.
So in this theory, often you treat MG more like as a closed subarray. I mean, you like to replace MG, but it's a risky closure sometimes in AG.
Yeah.
When you do this lifting, how can you be sure that you don't lift to the boundaries of MG, so you get the kind of a Jacobian of a reducible curve? How can you be sure that you're really inside MG?
Somehow because you start with something that is already in MG mod P.
And then you can control it.
Yeah, and so somehow everything, once you, like you can phrase everything just on MG itself. You just have a VHS with the variation of Hodge structure on it and you do everything there. And you don't have to think about AG. AG is a kind of useful psychological crutch, but everything can sort of lives on MG. And so the argument doesn't see AG at all.
Thank you again.
Mm-hmm.